When you want to measure humidity and placing of your humidity sensor, you want to be aware of several external factors that you need to keep in mind. If you have a large room that you're trying to be measuring and getting an accurate reading of relative humidity, airflow is critically important. You don't want to be placing a sensor in the corner of a room if your product or material that's important to you is in the center of the room. If you have a clean room and there are cleaning crews that come in, you want to make sure you have known wash-down procedures. Is the cleaning crew going to slap the humidity transmitter with a mop, or are they going to spray it with a hose? Are they going to use solvents, which could add to sensor poisoning? Also, during placement of the transmitter, you want to be aware of external factors like windows, where there might be sunlight coming in. That could cause temperature effect. Opening and closing of doors can also affect readings. You might see spikes on your results. You don't want to place a sensor near any type of blower or HVAC duct. All these things can cause temperature changes, and as we just showed on the previous slides, if the temperature changes, then your relative humidity is going to change. In this day and age, there's all different types of shapes and sizes and models of humidity transmitters available. Humidity devices, from handhelds to transmitters to loggers and whatnot. We're going to talk a little bit about all of those, but we're also going to talk about the types of sensor technologies. What you need to know ahead of time is what are the external factors and temperature ranges that we just discussed. What is your desired operating range? Are you at a high temperature? Are you at a medium relative humidity range? Are you going to be measuring very dry conditions, parts per million of moisture? What are your tolerance requirements, and what are your accuracies? A 1% or 2% RH accurate unit is probably going to be a little bit more expensive to much more expensive than a 4 or 5% accurate device. And then choose the right technology. Do you need duct mounted? Do you need wall mounted? Do you need digital versus analog? Are you using resistive sensors versus capacitive sensors? What type of output signals? Again, analog versus digital. Do you need a display? These types of things need to be considered. And of course, how will you power the unit? Are you going to plug it into a 110 wall outlet, or do you have a low power option available? There's a whole plethora of different types of humidity sensor technologies that are out there. I was actually at a customer yesterday. It was an art museum. They had an antique, it looked like an antique. It was a horsehair hygrometer, which basically the horsehair, as humidity increases, the tension of that horsehair increases, and it was attached to a mechanical arm on the edge of a chart recorder. So those were the early days. Now there's really only a few more common, and those are based on polymer and aluminum oxide technologies. The first one we'll discuss briefly here is resistive technologies. These sensors are basically polymers that they are measuring resistance or electrical impedance, and the resistance changes inversely with the relative humidity. They're good because they're small, they can be inexpensive, they can be produced relatively inexpensively, and they can sometimes be interchangeable in the field. But what you're giving up is a bit of a limited range. If they get saturated, they are often damaged or need to be calibrated. They have a lot of temperature effect to them, so you would need to compensate for temperature effect on the sensor somehow. And they can often be sensitive to contaminants and whatnot. These are for, as you can see the range there, of from 15 to 95% relative humidity. As you get below 15%, the impedance is too large, and most circuits today can't handle that. Another type of common technology is an aluminum oxide or ceramic oxide. This really doesn't pertain too much to relative humidity. This pertains more to low dew point applications, or parts per million, or even part per billion applications. And it operates on a similar principle as to some other sensors, where you have a permeable oxide layer that's porous, water vapor pressure equilibrates into those pores, attaches to the side, and changes the impedance of the signal. And that can be characterized as a humidity curve. Some of the problems, again, with this is that if it gets saturated, you might be out of luck. The sensor might be completely damaged, or you definitely need to recalibrate. They're good for process control applications where you're going to be very dry, desiccant dryer applications, dry natural gas applications. But when we talk in terms of relative humidity, we're talking in a completely different scale, a wetter scale, and it doesn't really apply to these types of products. The next sensor that is becoming more and more dominant these days is what we call a capacitive-thin film polymer sensor. There's a whole bunch of different types out there, but very few manufacturers have a polymer that demonstrates all the qualities you look for in a relative humidity sensor. Why would you want to use a polymer percent relative humidity? Basically, it is measuring capacitance based on the difference of dielectric between dry air and moist air. The dielectric of water is 80, and the dielectric of air is 1. So basically the design here is a parallel plate capacitor that gives you good linearity, good temperature coefficients, and good recovery from condensation on some capacitive sensors, not all. This slide just sort of blows that out. In the center here, you have your polymer material surrounded by a sandwich of electrodes. In this case, it's porous platinum. And then oftentimes manufacturers will provide an additional layer of protection, and in this case it's a porous Teflon filter on the ends. All this together measures about 0.008 inches of thickness, so it's very thin, therefore very fast responding. It has airflow on both sides of it. In this example, you can see that this particular capacitive sensor is very, very linear. You can see down from about 285 all the way up to 340 picofarads. It's very linear, and then today's digital electronics allow you to enhance that linearity or even better to give you better accuracy. This chart just gives an example of some of the chemicals and some chemical resistance. Although, typical things that attack metal leads and whatnot still apply here. Acids and things can be dangerous. But the polymer itself is actually quite resistant compared to other polymer sensors against some of these various chemicals and solvents. So what's new in the market today for digital sensors? The digital technology has really advanced the product line quite a bit. There's only so much you can do to the actual sensors, but the surrounding electronics have actually become quite powerful today. Nowadays, you can find manufacturers that provide you with somewhat of smart probes. On the probe itself, you will have a microprocessor, ASIC, and EEPROM combined on one chip. And what that will allow you to do is basically you now have a hot swappable probe. And that comes in big in the service areas. And we'll talk a little bit about that further on, but you no longer need to pull off the whole transmitter off the wall to do a calibration. You can just swap the probe because the probe now stores all the calibration data for humidity and temperature. The probes can now have onboard data logging, so you can record events or spikes or any problems and download that information and set that up in reports if you had to report to the FDA or whatnot. There is now technology that allows for self-diagnostics. Basically, they're internal signals that the sensor will check itself against, and if it falls without a certain tolerance, then the curve can actually be automatically adjusted to come back into tolerance. Fixed simulation means you may know that your sensor has a fresh calibration on it, but how does your control loop know that it's working? You can now program these smart probes to know or for a fixed value of temperature or humidity, so you can check your entire loop. You can get other psychrometric calculations such as dew point directly from the probe. We can now easily eliminate temperature effects. On this particular probe, there's over 30,000 points of temperature compensation. That means not all applications are at 20 degrees Celsius. Sometimes they're at 40 degrees Celsius, or sometimes they're in cold rooms down at closer to 0 degrees Celsius. Every sensor has temperature effects, but now we can compensate for those effects by adding in temperature compensation on the probe itself. You now have improved calibration capability where you can do multiple points at once. You can do any sequence at once. You don't have to do a specific humidity point and then do a specific cadence of points per the manufacturer. Is now opened up where you can do one point come back a few days later and do another point. It's much more simple with the digital technology. And of course, all systems can be tied into a validated system that meets FDA requirements.